Okay, recording is rolling. Welcome to Wednesday, November 10. You guys know that tomorrow is Veterans Day, so I won't see you guys. Friday, we're going to do a lab we're going to break up those bouncy balls, and you guys can measure how bouncy those are. It's called coefficient restitution. But here's what we're doing today. We're going to clean up some stuff that didn't quite get to so far. So there's one more problem in the homework we got to do. There's also a quiz question I asked you guys that I realized hadn't showed up on any of the materials so far, so I'll cover that. It's a ballistic pendulum. It's a real classic physics question. Then we'll do those conceptual questions on Kahoot, which some of these show up on your quiz too. I think I told you guys this yesterday. Uh, I have returned your guys' energy quizzes, so those are in those folders. So if you want to pick those up at some point, right? You guys know you got a couple things due coming up. The momentum homework, which of course we're going to finish in class today. If you want to turn it early, feel free to. Otherwise, I'll pick it up on Friday. And you guys do have that open notes take-home quiz that is due on Monday, right? You guys good so far? Right, so let's go hit that last homework problem that number 74 from chapter 9. That actually we started the other day, but just the bell rang on us before we were able to finish this. And so I'll do this a little bit faster than I usually do, just because you guys probably have half of this in your notes already. You guys remember there was marble C and marble D, and they were colliding. And well, there are a bunch of little questions, but it all sort of leads up to this last question: is what's the post-collision speed of marble D? Okay. But all these middle questions are kind of interesting because they maybe help you see the big picture of the conservation of energy, or sorry, conservation of momentum framework, right? It's a collision. We're got to do conservation of momentum. Okay. So the first part said just draw a before and after picture. So you probably have this in your notes already. So sketch this up real fast. There was marble C and marble D, okay. And this guy had a mass of 5 grams. The marble D was twice as massive, 10 grams. And they were each in motion, but with different velocities. So velocity of marble C initial, and by initial I mean pre-collision, was given as 20 centimeters per second. Notice they're using grams and centimeters in this question, but you guys did that too with that elastic collision lab. Well, actually, just with those collision carts, you guys did elastic and inelastic in both cases, using centimeters and grams. Okay, velocity of marble D initial was given as 10 centimeters per second. Okay. This was all pre-collision. Okay. So if you prefer this model, it's sort of like a car is going to rear end a van that's moving slower. So bam, something like that. Bam. Okay. They're going to bounce off each other. Okay. I bet this will probably be pretty close to the elastic side, but maybe not perfectly so. Right, then, bam, these things collide, and after the collision, we're going to have marble C moving at only at 8 centimeters per second. This is velocity C final, like post-collision. Okay. And marble D is going to be, well, we don't know how fast it's going. Well, we don't yet anyway. That's sort of where this is all leading. This is all post-collision. Post-collision. Right? You guys got that? Okay. Now, even before we start this, what a good idea is to do is to see the big picture of this, think, well, what are some reasonable possible answers? And if marble D was going 10 meters per second, it gets a bump from behind. This answer better probably be faster than 10 centimeters per second, right? If it was going that fast, better get a little boost. Okay? I hope so. Okay? What's that? So that was part A. Part A was just sketch that picture before and after. Part B says calculate each momentum before the collision. So before collision, we're going to just focus on this picture for part B. So momentum of marble C initial was, well, mass times velocity. Wouldn't that be 5 grams at 20 centimeters per second is like 100 gram centimeter per second. Okay. And marble D before the collision was 10 grams, moving at 10 centimeters per second. Was also 100 units of momentum, gram centimeter per second. Okay. question C and D say calculate the momentum of each one afterwards. So marble C, momentum of marble C post-collision is, well, okay, now we need the post-collision picture. Okay. We got 10 grams moving at 8 centimeters per second. No, scratch that. 5 grams. 5 grams moving at 8 centimeters per second. That's going to bring up to 40. Hello, Mr. Griffin. Okay, she'll know where to go. All right, I'll send her. Isabella Schiffer, Miss Armstrong is looking for you back at building 1. Miss Armstrong? She said back at building 1. She said you would know where to go. Tell you what, go to the office, ask for Miss Armstrong. They should be able to direct you there. Yeah, I don't know what the meeting's about, so probably a good idea. Right. But yeah, I'll post this video later. Right. So that was 40 units of momentum. Right, yes, sir. And then question D says, what's the post-collision momentum of marble D? Okay. And you might think, well, we've been doing mass times velocity, and we don't even know what the velocity of marble D is after. And that's wait, hold on. There's momentum accounting. Here's before the collision. Here's after the collision, so pre and post collision. Remember how the momentum has to be conserved? That's the entire premise of how we're solving these things. Guess how much momentum do you see before the collision collectively? I see 200 units. There better be 200 units after, which means how much momentum went into marble D? 160. Okay. So whatever actually we do know the mass. Mass is 10 grams. Okay. Times V of marble D post collision has to come out to 160 gram centimeter per second, right? So that these two add up to 200, just like these two add up to 200, right? Isn't that the whole premise of what we've been doing? Sum of momentum initial equals sum of momentum final, right? You guys get that? And so last question is, what is, let me slip in one little detail right here. Here's what I was just saying. Sum of momentum pre-collision equals sum of momentum post-collision. So 200 units equals 200 units. That's how you know this has to be 160, because that plus 40 would bring you up to the original 200. So last question. What is the post-collision velocity of marble D? Well, don't you just divide down the mass of 10 grams? Grams cancels. It looks like velocity D post-collision must be 16 centimeters per second. Right? Is that okay? Oh, and before we even started doing any numbers, remember how I said, well, it better be faster than the original 10 centimeters per second? And it is. It is faster than 10. I mean, it had to have been, right? Okay. And that's how the momentum is going to add up. Right? Let's go back. Now there's a sort of addendum I want to throw on this, which is I want to compare kinetic energy before and after. Right? So before the marbles collided, there was a certain amount of kinetic energy in the system. And after they collided, well, there's also kinetic energy. They each had mass and their motion. Okay? Now, the kinetic energy after compared to before, after the collision, is it less than, equal to, or more than it started with? The kinetic energy. Actually, there's two possibilities out of that. Right? So it's possible that they could have the same kinetic energy collectively after compared to before, but only if it's what kind of collision?
Elastic.
Yeah, elastic, like perfectly elastic, right? So maybe, I don't know, we're about to find out. We're going to run the numbers, right? If it's not that, then what is it after? More or less than before? How about this? What about inelastic collision? What if you have, like two balls come this way, a lot of kinetic energy, dead stop, zero kinetic energy. Oh, well, that would be decreased, wouldn't it? Okay, so it could tend that way. Okay? So what it can't be is more, okay? Unless, of course, you have like a grenade or you're throwing a ball or the energy comes from somewhere else. Okay? But just things colliding, okay? It's got to be less after compared to before. Now, we just solved for this number, and we got this to be 16 centimeters per second. So I'll go ahead and run them. Here. What is K naught and what is K final? So kinetic energy initial, say before the collision was, let's see, 1/2 mv squared, right? You guys remember that? 1/2 times 5 times 20 squared, 20 squared, plus 1/2 times this m times this v squared. Right? That looks like the number is 1500. Now that's not exactly joules because I'm using centimeters and grams instead of meters and kilograms, but 1500 something. Right? Units of energy. What is K final? Let's say units of energy. Okay. K final. So 1/2 times this m still 5 grams times this v squared plus 1/2 times this m still 10 grams times this v that we just solved for squared. Okay. Now when I hit enter, the number on my screen, let's see if you guys are following. Is the number on my screen going to be more than or less than 1500? It's got to be less than 1440 units of energy, right? Which, yeah, that is less than. It's not very much less than. So, looks like that collision was pretty close to the elastic end of what it could possibly do. Yeah. Yes, go All right. The other problem I have to talk about with you guys is ballistic pendulum. Now, this is, I've got an animation for you guys. Here we go. Ballistic pendulum. Oh, let me share my screen for the video. Share screen. Whoa, screen 2, share. Okay, now we're doing good. All right, so here's a really classic physics question that involves this ballistic pendulum. Okay, so we've got this bullet fired into this block. It swings up to, well, on that animation they're showing some angle it swings up to for a pendulum of some length, but that would be a height change also, wouldn't it? Like that block swings up some height change. Okay. Now, what question could you ask about this? Well, you can ask a lot of questions, right? Depending on what variable is unknown. Okay. But there are some things that are easily measurable, and maybe something that would be a really good question. So the length of that pendulum, probably pretty easily measured. That angle that it goes to, probably pretty easily measured. From that, you could get a height change if you remember. You guys remember like the chimpanzee swinging from the vine? Question from last section. Okay. Actually, that problem is part of the solution to this one. Okay. How about the mass of the block? How about the mass of the bullet? You could just throw those on scale and get those. But a really opportune question would be, what is the firing speed of the bullet? In fact, this is almost certainly why this was invented, what it was used for. Imagine it's like 1800, right? You have a shiny new pistol. You want to know, what is the firing speed of this pistol? Okay. Well, how would you even know that back in 1800? Well, you have physics. You have physics back in 1800. So, yeah, you can make some mass measurements and some height change calculations and figure it out that way. That's what we're going to do. So the question is, what is the firing speed of the bullet? What is the firing speed? And the process we're going to use to solve that is going to be a two-part process, and we're going to solve it in reverse chronological order. Here's why. Because what we're solving for, that firing speed, is actually the first thing that happens chronologically, but it's going to be the last. It's going to be end result of whatever process we go through. Okay. So we're going to start with after the bullet has already embedded itself in the block and they swing up to some height change. Okay? Now, whatever speed you need here, whatever height change that it's going to eventually get up to, which is some measured value. Okay? There was some necessary speed to get it up to that place in the first place, right? Okay. And that is the same as that chimpanzee problem from last section. Say if you're like swinging on a vine, right? It's sort of in reverse, right? If you know your height change, you can figure out the speed at the bottom, and vice versa. Okay. Then you say, well, where did that speed come from? Well, it came from the collision of the bullet with the block. So then we'll take one step back in time and say, what type of collision physics led to that? And that's conservation of momentum. So the two parts are going to be conservation of energy. That's the last thing that happened. Yeah. And then conservation of momentum for the collision. That's the previous thing that happened. And that'll lead us straight to solving for the firing speed of that bullet. Right, so switch back over. All right. So ballistic pendulum. So I got, there's some block here, right? Let's give it mass capital M, right? And there's a bullet, I'll give it mass lowercase m, that's fired at some speed, I'll call V bullet. Right? And that's the question, is like, well, what is that firing speed? So that it's going to kick this whole block up. There's a bullet block system, if it's embedded, right? To, well, pendulum of some length, it's going to swing up to some angle, right? I bet you could calculate a height change from that, couldn't you? Call it h, or some height change, right? Okay. Now, L and theta, if you know those two, you could figure out h. It's just equal to, you remember this from before, L times 1 minus cosine theta, if you follow through on the geometry, if you do a bunch of geometry. Okay. Now, the way I gave this to you on your take-home quiz is I went ahead and just told you what that height change was, just to give you guys a step. Okay. So, part 1, this is going to be a 2-part process, is to apply conservation of energy. Apply conservation of energy post collision. Okay, so just to swing from here to here, right? How fast did this have to start swinging to swing up to that height change? Okay. Guys, what kind of energy does this block have at the bottom? Kinetic or potential?
Potential.
If it's moving really fast, the bullets hit it. It's on the move. Yeah, that would be kinetic, right? Okay. And then when it swings up to some height and comes to a temporary stop, it has no kinetic up here because it's not moving, but it does have a height above the lowest point, so it has potential up here, right? Do you guys want to solve this in terms of variables for a general solution, or do you want to solve this with numbers? Numbers? Okay, sure, let's do it. Okay. Let's call this block, say 5 kilograms. We'll call the bullet like 0.1 kilograms, and we'll call the height change, since okay, we'll call it 0.25 meters. Right. Let's say that's right. And then you guys know G is about 10 meters per second squared. Okay. All right, so we're going to have 1/2 mv 1/2 mv squared. Okay. Now you have to know what is the m and what is the v. So this is after the collisions happened. If the bullet's embedded in the block, that's why it's the sum of the masses. Okay. This is post collision squared is equal to mgh. mgh, right? Kinetic discharge of potential. That's just your classic pendulum, just like you guys saw last section. Okay? Now, even if you miss the detail about what mass is relevant, you guys see it's going to cancel out anyway. Right? And suppose we're going to solve for this right here. Now, this is not the firing speed of the bullet, but it's going to help us get there, right? Okay. Ooh, do you guys see that V post collision? It's just going to be here, 2 other steps times 2 square root 2gh. Okay? And I make that point in terms of variables because this is something that keeps coming up over and over and over in the class. You saw the kinematic motion. You guys saw this conservation of energy. Obviously we just applied that. Okay? It's one of the things that keeps coming up over and over in the class. Okay? All right, now let's plug in those numbers and get an actual speed. Like how fast was the bullet swing to swing up to that point? That'd be square root of 2 times 10 meters per second squared times the height change of 0.25 meters. Right. 0.25 meters, you guys know that's 25 centimeters is most of the length of this roller, right? There's 25 centimeters. So if you have that height change, all these numbers, right? See what it comes out to. Square root 2 by 10 by 0.25. I'm looking at 2.2 36. That'd be meters per second. Now that is not the answer to the question, but I should dash outline that. Okay. That's definitely a critical middle step. Okay, so that's how fast this bullet block together started swinging up to reach that height, right? Okay. That's part one. You guys ready for part two? Okay. Now we're going to go further back in time to get to part two. So part two is chronologically what happened first. Apply conservation of momentum for the collision. Sum of momentum before the collision equals sum of momentum after the collision. Okay? Now, where did all the momentum come from? Well, it came from the fact that the bullet was in motion. So it all came from the bullet. Mass of the bullet times velocity of the bullet. Here's what we're actually solving for now that just appeared on the map. Right? Mass of the bullet times velocity of the bullet, right? Plus mass block, velocity block, but that was just zero because the block was just hanging at rest, right? Is equal to, this is inelastic collision, isn't it? Inelastic. Block plus bullet times the post-collision velocity. Post-collision. Right? Sure. And post-collision velocity, we just figured that out. That's just this right here. We did all that conservation of energy stuff like with the swinging pendulum to figure that out. So let's plug in those numbers. I said the mass of the bullet was 0.1 kilogram. Velocity bullet, solving for, is equal to, all right, mass of the block was 5 kg, bullet was 0.1 kg. All right, and then V post-collision, that's your 2.236 meters per second. Right? Guess you one algebra step to get to the answer. Divide both sides by the mass of the bullet. Right? So velocity bullet is, right, what is, see, 5.1 times 2.236, all divided by 0.1. I'm looking at 114 meters per second. Okay? So whenever you see ballistic pendulum, which is that category problem, usually the question is, what's the firing speed of the bullet? I mean, I'm sure that's what this was originally invented for back in the day. Kind of makes sense. Okay? And yeah, two parts. You have to solve it backwards in time, right? Like reverse chronological. First, start with the swinging pendulum part, which is conservation of energy. Get some square root 2gh expression. Okay? And then go back in time one more step, conservation of momentum, collision, and get that firing speed.
Five is the block, the mass of the block.
Yeah, 5 kilograms is the mass of the block. Yeah. Yeah. All right. You guys get that? All right. Let me glance at you guys' quiz, make sure. Okay, we're about to do Kahoot, some of these conceptual questions you're about to see. The ones in the back, we just did ballistic pendulum, so you should be able to get that. These three questions, 7, 8, 9, I pulled straight off this gridded half page that I went over with you guys in the notes. So as long as you took good notes, you should be able to get those, no problem. Now this page I'm not going to pick up for points, but that's some really good fundamental examples. The other sort of tough problem that I'll give you guys a little pointer on right now is number 6, hitting a ball with a bat. Okay. So what I want to mention about this is, you guys know, well, obviously that most recent poster I hung up, this is going to be an impulse question. Okay. So force versus time, that's how you know, because what property of force versus time tells you impulse? All right. Here. You guys remember this right here, right? You guys remember that? Okay. All right. Here's the other detail that matters. Impulse, momentum, velocity, force, all those are examples of vector quantities, which means that direction matters. So in the setup here, we're saying the pitcher throws the ball at this speed towards the plate. I guess speed is a scalar, just tells you magnitude. And then the batter's going to hit it in the opposite direction. Right? Do you think that there is some negative sign that needs to be put in somewhere? So somebody needs to be negative, right? Okay. Okay, I'll throw that at you guys. I think you guys can get that from there. Just give you that little hint. All right, guys ready for a Kahoot? We switch my screen over. Say present screen to share. All right, and then play Kahoot. All right. You guys got a new 7-digit pin. All right, you guys ready to go? So if you're half a minute late, that 7-digit pin will be bottom of the screen. All right, and here we go. The momentum of an object is defined as the object's mass times velocity. Oh, one winner. You guys, mass times velocity. That's what we've been doing the last couple of weeks, right? Mass times velocity. Right, that's what all these posters up here say. Mass times velocity. Guys, what is the code? Where'd it go? Oh, here it is. 598-4450. Okay. Right, some of you guys pick the blue one. Guys, what is velocity times time? What is that? Guys, if you're driving your car at 60 miles an hour and you do that for 2 hours, what does that tell you? How far you've gone? Like displacement? Right? What is mass times acceleration? What is that? Force. Yeah, that's Newton's second law of motion. That's force. Right? What is force times acceleration? That is a junk answer. That ain't nothing. We got Joshua picking up all the points. Got monopoly. If the momentum of an object changes, mass is constant. What else is true? Yeah. Right. So if the mass is constant, then velocity must be changing. But if velocity is changing, that means it's accelerating. And if it's accelerating, that means there's a force on it. So these options, if any one of them is true, then they're all true. They have to be. Yeah. You guys got that. But Joshua, Matthew, Bridget, Carl, Olivia, all getting points now. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher is. The same. Guys, this is where have you guys seen this before? For every force, there's an equal and opposite reaction force. Oh, this is Newton's third law of motion, isn't it? This is a real old classic question. Why is that showing up here? Well, take a good look at this impulse poster up here. So you guys do see that the force on the ball and the force on the launcher would be the same, right? Do you think the time interval that acts for is also the same? Right. Now, why am I pointing that out? Well, that might be coming up right here. We've got, so same scenario compared to the impulse on the ball, the impulse on the launcher. It is the same, right? So if it's the same force for the same time interval, then yeah, the impulse has to be the same. That's to say that whatever the mass times velocity of the ball is sent off one direction, the mass times velocity of the launcher is sent off the other direction. Right? You know what this kind of reminds me of is, you guys remember Magic School Bus clip? Wanda throws the baseball, gets kicked back towards second base. Right? Isn't that like physically the same? Sure is, isn't it? We got Joshua on fire, Bridget, Bella, Carl, Olivia. A collision is considered elastic if Yeah, there you go. All the above. Right. So the definition sort of is like the kinetic energy is conserved, but that would imply that there's none of the energy went into force times distance of deformation. Right. And obviously sticking together would be inelastic, which is the opposite of elastic. So there you go. Elastic fate Newton's cradle. So. We're all standing on a pond. There's no friction between her feet and the ice. How can she get off the ice? Yep. You have to throw something out the opposite way, right? Or maybe swim against the air, maybe, but you can't push against the ground because there's no friction to push against. Yeah. You guys remember Magic School Bus clip? This kid's trying to run around the field. They were not having such good success unless they threw something or something climbed into. Right? Freight train rolls along the track with considerable momentum. If it were to roll at the same speed but had twice as much mass, its momentum would be. Okay. Twice as much, right? Okay. Switch over. Write this down for you guys. So, you guys remember how momentum is equal to mass times velocity? Right? So, if you double the mass, then wouldn't that be doubling the momentum? Right? There's a direct relationship. Okay. And if that's not super clear, then you can always make up numbers. So, what kind of 1 kilogram moving at 1 meter per second? Wouldn't it have like 1 kilogram meter per second of momentum like that? Okay, so then what if you went back and you doubled the mass to 2 kilograms? Then you kept the same velocity. Right? Wouldn't that be twice as much momentum as before? Right, guess yeah. So direct relationship. Nothing's being squared, nothing's being divided. We got Joshua, Matthew on fire, Bridget, Bella, Olivia. Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small. Because why? Yeah, cannon has so much mass, has so much inertia, right? So you guys know the forces are the same, equal and opposite. You guys know force times time, that's what impulse is, right? Or mass times change of velocity. That's also equal for both the cannon and the cannonball. They get the same impulse, they get the same change of momentum. Well, just opposite directions, right? One's positive, one's negative, right? So that's equal, right? Okay. But the cannon has so much mass that you take that impulse, you divide by a huge mass, that's a very small change of velocity, right? Or the old way of thinking about it was has so much inertia that the acceleration would during that explosion would be very small. So however you think of it. Yeah. In order to catch a ball, baseball player moves his or her hand backward in the direction of the ball's motion. Doing this does reduce the force of impact. Why? Ooh, yeah, pretty good. Yeah, most of you guys got that. The time of impact is increased. Right. So this one I was gonna throw some notes at you guys anyway. So you have to think about it. So you guys remember how force times time interval, what's really average force, but whatever, results in some mass times change of velocity. Okay, this is impulse. The impulse formula right there. Okay, so say when you catch a ball, what's the mechanics going on according to this equation? Well, the ball has some mass. That didn't change no matter how you catch it. Also, the delta V does not change depending on how you catch it because the ball was coming at you some speed and you're bringing it to a full stop. So the delta V is just, just changing that speed to a stop. Okay. this is all some constant value. Right? The impulse is the same, regardless of how you catch it. Right? Okay, so how do you reduce the force on your hand? Oh, by extending the time of that impact, right? Here, I'll give you guys some example numbers. What if you had a 1 kilogram ball changing from 24 to 0 meters per second? So you had an impulse of like 24 Newton seconds. Okay? 24 Newton seconds. And what if you caught this ball all in, like, let's say 2 seconds? So a very, very long, right? 2 seconds. What would the average force be? I see 12 newtons. Okay, great. But what if you caught it differently? Now you can't change the impulse. Like same mass ball, same, still bring it to a stop. But what if you extend that time interval to 3 seconds? Now what's the force on your hand? Do you guys see it's 8? It went down, didn't it? Right? When two variables are multiplied together, same side of the equation, they have an inverse relationship with each other. Another thing you could have done is just divided the delta t over. Maybe you prefer to say it that way. So different ways of explaining things, right? Yeah. By extending the time interval of the collision, you decrease the force. There you go. Got Joshua, Bella, Olivia, Kaylee, and Matthew. Car traveling along the highway needs a certain force to stop. More stopping force could be required when the car has. Yeah, okay, you guys got that. It's not a trick question, those are just all true statements. Now you guys do know that if you wanted to solve for stopping distance, the mass of the car would cancel out, blah, blah, blah. But yeah, force to stop, sure. These are all true. We got Joshua, Bella, Kaylee, Matthew, Bridget. The force of an apple, I like this question. The force of an apple hitting the ground depends upon. Ooh, nice. All the above. Right, you guys got it. Right. So switch over here. You guys remember how F delta T equals M delta V? Right? What if I want to solve for that force? Go ahead and rearrange this equation. M delta V over delta T. Go like that. Right. So we've got the mass of the apple. Right? That is whatever it is. Okay. We've got, how about delta V and delta T, right? So here's the crash speed. V crash, probably V not, right? And then boing, right? Maybe the apple rebounds, maybe not, but let's consider both those cases, right? So V final. Right. So the mass of the apple matters. How about change of velocity? Hey, what if, here, here's some example numbers. What if the crash speed is like 10 meters per second and the rebound speed is like 5 meters per second? Right. But change direction, right? Okay. Who can tell me what the delta V is for that scenario? What's the delta V? And it's not 5, it's what? 15 meters per second, right? Because 5 up minus 10 down, what's the difference between positive 5 and negative 10? It's 15, right? So, but what if the apple had not bounced? What if it just went, just splat? Wouldn't this number go to 0 and the difference actually would be 10, right? So, okay, so whether or not it bounces affects this right here, doesn't it? Okay. And then here's the time of collision for impact. So this might be a tiny fraction of a second. Okay. Yeah, so all those variables are mattering. Switch back over. All right, we got, all right, so speed before it hits, time of impact with the ground, and whether or not it bounces. Yeah, those would all matter. Got Joshua, Matthew, Bridget, Carl, Israel. Moving freight car runs into an identical car at rest on a track. The cars coupled together. Compared to the velocity of the first car before the collision, the velocity of the combined cars after the collision is. Yeah, half as much. So, here. cart, mass M. This guy had, call it V naught. When they come, you guys remember inelastic collision? I'm thinking about this one right here. Okay. So what was the sum of momentum initial equals sum of momentum final? I had some mv naught, and then it's going to be m plus m. Isn't that like 2m times vf? Okay. So you guys see a 1/2 v naught equals vf. There you go. That's it. That's the whole thing. Next. Okay, we're getting a little short on time. I'm gonna try to do this a little faster. Piece of putty moving with 2 units of momentum strikes and sticks to a heavy bowling ball. After the putty sticks to the ball, both are set in motion with a combined momentum. That is, I mean, if momentum is conserved and it's inelastic, this is not a trick question. You have 2 units of momentum before the collision. You must have 2 units of momentum after the collision. It's just conservation of momentum, perfectly inelastic. Right? Momentum is conserved, 2 units. Okay. All right, now here's what that leads up to, though. I've got a slightly different question. It's a little bit trickier. A bouncy ball with 2 units of momentum. The bowling bounces off a bowling ball at rest. Okay. Now, just the bowling ball itself is set into motion with how much momentum? Ooh, yeah. More than 2. Okay, here's why. Okay. Suppose you got, okay, switch over. Okay, here we go. 2 kilogram meter per second. This ball goes boing. Okay. Let's suppose it rebounds at like half the speed. So -1 kilogram meter per second would be its momentum, right? Okay. I see that the delta P is in like 3 kilogram meter per second. So what does the ball roll off with? 3 kilogram meter per second. Yeah. Or if you prefer, sum of momentum before equals sum of momentum after. There's 2 units there. What's 3 minus 1? 2. So see how it's conserved? 2 is equal to 2. Right? So that bowling ball rolls off even faster. Now there's a limit. There's an upper limit to this, right? You can't get too crazy. You can't violate conservation of energy. So it couldn't be like, well, oh yeah.
Can you
Uh-huh.
explain the last question?
Wait, what?
The last, the one with the putty.
Oh, the one with the putty?
Yeah.
Right. So the whole deal with the putty was if you got some putty, let's move with 2 kilogram meter per second.
Yeah.
Right? And it goes collides with the bowling ball. They roll off together with 2 kilogram meter per second. Sum of momentum before equals sum of momentum after. That's it. Right. So that was really just to provide a base example for to contrast this against. Right? If the bowling bounces off, this one takes a little bit more thinking. All right. The force that accelerates a rocket into outer space is exerted on the rocket by the exhaust gases. Everybody just pick exhaust gases. Gases go one way, the rocket goes the other way. Woohoo! Yeah. Next. Yeah. Thank you. Cannon shot from a long barrel travels faster than one from a short barrel. Like, why do rifles have a really long muzzle? Why do artillery have a really long muzzle? Because there's the same force on whatever's being shot. But doesn't the longer rifle give a longer time interval, therefore a greater impulse? Exactly. 2 kilograms thrown at 3 meters per second. What's the momentum? 2 times 3 is 6. 2 times 3 is 6. What if you got 4 kilograms with a momentum of 20 kilogram meter per second? What's its speed? What's 20 divided by 4? 5, or 5 times 4 is 20. What if something's moving at 6 meters per second and has a momentum of 24 kilogram meter per second? What's its mass? 6 times what is 24? 6 times 4 is 24. Okay, how about this? Which delivers more force? When you have the inelastic collision or you boing bounce off? You guys remember that apple bouncing against from the ground? Wasn't there more force associated with bouncing? Yeah, if you have to watch this video after the fact and get a closer read on that, there's more force associated with bouncing. Okay? Okay. Now, the Earth already spins eastward, so what if everything on the surface started walking eastward? What would happen to the ground beneath them? If the Earth is already spinning eastward. Okay. This could be weird, but you guys got a long time on that one. Here, let's catch this up for you guys. Here's the Earth. Okay. It's already spinning eastward. If everybody starts walking eastward, aren't they going to push the ground beneath them like westward? And would that slow down the Earth just a little bit? Okay. Now, the Earth and everything on it is a closed system, so that wouldn't be permanent. If everybody came to stop, the Earth would just go back to what it was doing. Okay. But yeah, that's the sort of short answer right there. All right, with the bronze, Bella. With the silver, Bridget. With the gold, Joshua. You are runners up. Got Olivia and Israel. All right, nice job. Oh yeah, we fits in. A few more seconds of class. All right, anybody got any questions from today?